and I think we'll catch on fairly quickly. We're just going to go over some graphs initially, and then we'll get into the good calculus stuff. Alright, so last year in pre-calc you guys learned quite a bit about trig, sine, cosine, tangent, their reciprocal functions, their graphs, some identities, all good things. But I'm also pretty sure you talked about their inverse functions, like arc sine and arc tangent, arc cosine. Do those sound familiar?
Yeah.
A little bit too? Okay, another way you might see those written. So for instance, arc sine of x is the exact same thing as inverse sine of x. Maybe you'll see the little -1 power signifying an inverse. They mean the exact same thing. So we'll get into some of those examples, at least in the derivatives boxes at the bottom. But notice how this graph says arc sine, arc cosine. That's the same thing as sine inverse or cosine inverse. Okay, so I'm hoping that these graphs on the left-hand side look familiar. I know in the past you've graphed sine, cosine, tangent, and maybe even their reciprocal functions. But I want you to realize that if we know what the graph of an original function looks like, can't we then simply switch the ordered pairs and we would then have the graph of the inverses? Didn't we do that before? The whole idea of an inverse is to switch x and y. So notice how if you were to take, let's see, this ordered pair 0, 0 and switch it, wouldn't it still be 0, 0? All right, so that's on the inverse graph right there. Notice how this maximum is at pi over 2, comma 1. So if you switch that, you would be at 1, comma pi over 2. Maybe you wanted to go the other way. This minimum right here is negative pi over 2, comma negative 1. So if we switched it, we would have negative 1, comma negative pi over 2. Now if you kept going, this inverse graph would also be a wave. Okay, so you would be able to fill it in kind of like that. But what's the issue with that wave? What do you think, Braden?
It's not a function.
It's not a function. It doesn't pass the vertical line test. So what we do is, in order to make it a function, we erase certain portions of it, specifically this top portion and bottom portion. That way we're just left with this little piece, and doesn't the vertical line test pass that section? So what we're doing is we're only analyzing this section of the sine graph, and that's giving us this section of the inverse sine graph. Okay? The same thing's going to happen for cosine. What we're doing is we're only going to take this little section of cosine, and if we were to switch all of those ordered pairs, we would get this graph. Same thing with tangent. If we were to just take this middle section and switch the ordered pairs, we would get this graph. Okay. Now notice how tangent has vertical asymptotes at pi over 2 and negative pi over 2. So if you were to switch to the inverse graph, those vertical asymptotes would now be becoming horizontal ones. So we do have some horizontal asymptotes on the inverse tangent graph. Do these kind of look familiar? Maybe, slightly, maybe, maybe not. Okay, we're not going to be spending too much time on graphs. I just want you to kind of show you where these inverse trig graphs come from. For arc cotangent, we're taking this section and flipping it, so that would look like this inverse graph. This one, though, has asymptotes at pi and 0. For inverse cosecant, a little different. We're taking one section of the one parabola and merging it with the other section from the other parabola, and that's what's creating this shape. Notice how if we had a vertical asymptote at 0 on the original function, it's now a horizontal asymptote at 0 on the inverse if you switch it. And then for cosecant, we're taking this section from the one parabola and this section from the other. And if the asymptote for this one was at pi over 2 vertically, that's where it is now horizontally. Okay. So just little tidbits about where these inverse trig graphs come from. What we're going to spend most of our time on, though, are the derivatives. Okay, so it would be nice for us to at least recognize the graphs. That's just about it. We're not really going to use them for anything. But just recognizing which one is inverse sine, inverse cosine, inverse tangent, inverse cotangent, that's basically the gist of that little piece. Okay, just recognizing which graph is which. All right, so in terms of derivatives, these are going to look very, very weird. I'm going to tell you right now that inverse sine and inverse tangent are the two popular ones that kind of show up a lot, at least on quizzes and tests and AP tests and such as life or with those. But we are still going to go over the other ones because I think they're at least worth noting. Okay, so what I'm going to do is I'm going to write down the derivative shortcutter rules, and we're simply just going to practice 3 examples. If we need more practice, we can do some of the homework problems. But I think you guys are going to catch on really quick with these, at least on how they operate. So maybe 3, in my opinion, should have been enough, but if it's not, you just let me know and we can do more. Okay? So let's take a look at the trig shortcut or the derivative shortcut rather, for inverse sine, or in other words, arc sine. If you want to write that down too, it means the same thing. Notice how we have that symbol d over dx, that symbol signifying the derivative of this equation is blank. So that's what we're going to fill in. So I'm going to write in the shortcut, and I want you to kind of think about what it's saying. It's going to look weird, I'm telling you now.
So x to the power of 1?
That is an x prime.
What?
I know.
That is x to the power of 2, correct?
And that's next to the power of 2. All right, so we're going to label what this is representing and what this is representing, because I think we're good with the other stuff. We have division, we have 1, we have square root, we have minus, okay? But when you take a look at x prime and x squared, how does that relate to the x value in the original equation? What does prime normally mean? Like if we said f prime of x? Derivative. That little apostrophe prime symbol means derivative. So what this x prime is telling us is whatever is on the inside of this trig function, because if you take a look at some of the examples at the bottom, do you see how the 3x is on the inside, the 2x squared is on the inside? Okay, whatever's on the inside of that inverse trig function, that's what you need to take the derivative of. That's what the x prime is signifying. So we'll label this derivative of inside. What do you think the x squared is symbolizing? Yeah.
The shape it's going to make in a sense.
What do you mean by shape?
Like the way that the numbers are affected.
Okay, so you're squaring it, you're affecting the numbers somehow. Okay, so if this prime is meaning the derivative of the inside, doesn't this squared mean to technically, for the lack of a better word, square the inside? Okay, so we're going to go ahead and square the inside, specifically affecting them in some manner, like Dan was saying. All right, so as we go through some of these other shortcuts for the inverse trig, you're going to see some squares and you're going to see some prime marks, and that's what all the other ones mean. Okay, let me ask you this. If the derivative of sine is cosine, right? We know that. And the derivative of cosine is negative sine. Okay, maybe there's a connection between the two that you can think of. If this is the derivative of inverse sine, what do you think the derivative of inverse cosine is? If you can use the regular trig derivatives that we know and somehow relate it to the trig inverse ones, yeah?
X prime over square root of 1 plus x squared?
Good guess. Did you have a guess, Vinny? No? You changed it? Okay. You had the right idea of flipping something, you just flipped the wrong thing. We're going to have the same exact derivative, just negative. You know how sine, the derivative is cosine. And then for cosine, the derivative is sine. Okay, they're basically the same mirrored relationship, just one's positive, one's negative. Right? Same thing's kind of going to go on here. We have the same derivative going on, just one's positive, one's negative. So, if you know what the inverse sine derivative shortcut is, you already know what the inverse cosine derivative shortcut is. So you get a kind of a 2-for-1 special there. If you know one, you know the other. It just happens to be negative. Okay, so there's that prime symbol again, representing the derivative of the inside, and there's that squared again, meaning squaring the inside. All right, I'm going to go ahead and jump to tangent. I'm going to save the other two for last. Those are kind of special in my opinion, because they're involved. The derivative shortcut for inverse tangent, we have x prime over 1 plus x squared. Notice how it kind of looks similar to the inverse sine one, just a little different. We don't really have the square root anymore, and then now it's a plus instead of a minus, so there's a little difference between the two. Can we take a guess as to what the inverse cotangent one would be? We're educated in here. We can take an educated guess. What do you think, Dan?
Negative x prime over
There
1
we
plus
go.
x squared.
Uh-huh. Again, if you know one, you know the other. Okay, so this is where it gets good. The inverse secant and inverse cosecant, these are a little crazy in my opinion. We have x prime over, I don't think I have enough room in there, so I'm going to do it kind of sideways, a fraction. We have the absolute value of x times the square root of x squared minus 1. Again, these all look very similar. There's just slight differences between the two, or actually all three of them. If you know what inverse secant is, the shortcut, do you know what inverse cosecant is? Same thing but opposite. Alright, so I know they look intimidating, but in reality, if you know the left 3, you automatically know the right 3. Maybe another little shortcut to help you out here. Notice how all the trig functions that start with c, those are all the negative ones. Okay, kind of help you out. So what we got to do, if you need to reference this chart, that's fine. Hopefully you at least get familiar with these two, because those are the big ones that normally kind of show up. But what we're going to do is just practice using these derivative shortcuts on the 3 examples at the bottom. Okay, so I'll leave them up there so we can reference. Take a look at the first one. We want to figure out the derivative of inverse sine of 3x. So according to the shortcut, we need the derivative of the inside. Do we know what that would be? The derivative of 3x. 3. Okay, so that's our numerator. And then in the denominator, we need the square root of 1 minus the inside squared. So if you were to actually do 3x squared, what would you get? 3x times 3x. 9x squared. And there's your ending derivative. You can leave it like that. Not too bad, right? Okay, it's just understanding the setup, what the shortcut looks like, and then applying the correct derivative rules. All right, let's try tangent. So we're going to use that shortcut. Looks like the numerator is the derivative of the inside. So what's the derivative of 2x squared? Could we do that real quick? We got 4x. And then in the denominator, we need 1 plus the inside squared. So 2x squared times another 2x squared. Yeah. 4x to the fourth. And there's your done derivative. All right. Let's go ahead and try the last one. Okay, secant inverse. So this kind of crazy one in the middle with the absolute value. We need, first of all, the derivative of the inside. That's our numerator. So it looks like we would have 30x to the fifth. In the denominator, we need the absolute value of x. But remember, x is just representing what's inside the trig function. So that would be 5x to the sixth. And then we need the inside squared minus 1. So 5x to the sixth times another 5x to the sixth. 25x to the 12th. Okay. Now, maybe we can clean this one up a little bit more. Okay. Yeah, you want to give it a shot?
You can take out the 5, which will give you a 6 and the 6x to the fifths in the top, and x sixth in the bottom, which then you can cancel out the x's and get x times the square root of
there we go.
Whatever it is.
I know we have an absolute value down below, but you can still cancel things out in a fraction just like you normally would be able to. Okay, the absolute value just means that you have positive numbers down there. So we can still do 30 divided by 5, which gives us 6. We can do x to the fifth divided by x to the sixth, but we have 1 x left over inside the absolute values, and we're left with that square root. So that one you can kind of clean up a little bit more. Do you think those 3 examples were enough, or do we want to try a little bit more? We technically did the 3 shortcuts on the left-hand side, which means if you come across an inverse cosine, inverse cosecant, inverse cotangent, they work the same exact way. It's just you have a negative in the top. So I'll leave it up to you guys. Do we want to try some homework ones just for practice? Yeah? Okay. Let's go ahead and flip to page, I think it's 190. That's where all of the inverse trig ones are. Now I don't have the shortcuts listed on that page, so you might need to reference them to help you out. Are there any on that page that you kind of want to tackle together? Notice how if you look at them, it's a mixture of inverse and arc, but they all mean the same thing. You just want to go in a row? Do we want to jump around? Yeah. 13. Ooh, good. Okay. All right, so inverse secant. We need the derivative of the inside. Okay, that's our numerator. So what's the derivative of 3 natural log of x? Well, that 3 is a coefficient, so we can keep that. How do we figure out the derivative of a natural log? This was like our last section we did before inverses, or 2 sections before inverses. We did natural logs and exponentials. It's been a while. We gotta know our shortcuts. Other way around. You're close. Yeah, we have f prime over f of x. Or, sorry, we have, so we need, this is though if it was like the natural log of f of x. F of x is just representing the inside stuff. So what is the derivative of x? We just have 1 over the inside, which is just x. So maybe if you want to make note of that, the derivative of a natural log, I'll say in shorthand, is d inside over inside. D meaning derivative. All right, so that's the derivative of the inside of the secant function, but the rest of the inverse secant shortcut, we need the absolute value of the inside times the square root of the inside squared. So 3 natural log times another 3 natural log. You want to say that's 9 natural log of x squared. And then minus 1. Craziness. All right, can we simplify it though? Anything gonna cancel out or rearrange?
I guess you could get that 3 over x on the top.
Okay, so you could move the 3 to that top there. You could also cancel this 3 out with that 3 inside the absolute values. Those are gone. And then also, instead of having 1 over x divided by whatever's left down below, since this x is in the numerator, we can move it to this overall numerator, a property of fractions. Or you can think about bringing up the denominator and multiplying by the reciprocal, same idea. So in the end, we'd have 1 over x times the absolute value of natural log of x times the square root of 9 natural log of x squared minus 1. Absolute craziness. Okay, but again, this is not one of the common ones. Remember, sine and tangent, inverse sine, inverse tangent are the more common inverse derivative shortcuts. That was probably a good one to pick, Alexis. Are there any other ones that we want to kind of jump around with?
Well,
12. Ooh, this one's good. 5x sine inverse of 2x squared. How do we want to figure out that derivative? If you were to read it out loud, you got to be careful. Yeah.
well, wouldn't that just be a multiplicative, so you can just do like 5 pi 1, which would just become 5, then times whatever the derivative is?
If you're multiplying, you have to use product.
Yes, product.
Right. Okay, so this is really 5x times the inverse trig function. So we're going to have to go through our 1d2 plus 2d1 process. Okay, you don't just do derivative of one times derivative of other. Remember, that was Lillian or Lily, whoever from the test thought that that was correct, but you proved she was wrong. Okay, you laid down the law. So we have to go through our product rule. We have 1, and then we got to figure out d2. So the derivative of the inverse sine, we need the derivative of the inside, which is 4x, over the square root of 1 minus the inside stuff squared. So 2x squared times 2x squared, we'd have 4x to the 4th. So there's 1d2, but now we have to finish with 2 times d1, which would just be 5. So maybe we can clean it up a bit. 5x times 4x will have 20x squared over that square root. And then we can maybe move that 5 out front of the inverse trig function as a coefficient. All right, anything else you guys want to check out?
11.
11. We're just going to do the whole row. Okay. All right, so inverse tangent. We need the derivative of the inside. So how do you want to figure out the derivative of the square root of x? You could. Or how about we just rewrite it as x to the 1/2? This might be a little simpler. So the derivative of a square root, we'd have 1/2 x to the negative 1/2 over, so the shortcut for inverse tangent is 1 plus the inside squared. So if you square a square root, isn't that just x? Right? So if we clean it up, maybe, we can move the 2 to the bottom of the fraction, but also the x to the negative 1/2 to the bottom, because we have a negative power. So we'd have a 2 square root of x in the denominator, but we're still also left with the 1 plus x down there too. So if you want to leave it like that, you can. All right, I think we tackled the 3 hardest ones on there. I think you guys, I'm going to leave you to try the rest of the few, okay? What I want to do now is tackle one of your homework problems together, actually. So can we take a look at page 191? What we're going to be doing eventually, because we're getting into a lot of content so far this year, is looking at previous AP questions, like actual ones from AP exams that have occurred in the past. So for instance, this is the exact question from 2006. I know it was a while ago, but these 2 questions that they ask, I think we would be able to complete based off of what we've discussed so far this year. So I just want to go through kind of how we read one of these or how we tackle one, but we're eventually going to do these quite often, so we're going to get very comfortable with them. So the whole thing about a free response question is they normally give you some direction or tidbit of information at the top, and this information applies to every single part that you have. Not that you have to use it or you need it, but at least you know it applies to everything. However, the thing is, if you determine something from part A that might not be able to be carried to part B or part C. You know what I mean by that? Like, just because you get an answer from A doesn't mean you can use it for B. Sometimes you can, sometimes you can't, but you got to be careful. The only information that applies to everything is just what's at the top. So let's take a look at what we have here. The twice differentiable function. So we're going to take a look at that wording. If you see the wording twice differentiable, can you kind of think about what that means? Yeah.
We differentiate twice, or
okay.
You can go like to prime and into prime.
You can take 2 derivatives. Didn't we kind of mention that yesterday? How you can keep going in rounds? Okay. So you can take 2 derivatives. That's one good thing to know. Okay, there's only 2 derivatives, and then you're done, basically. It's not like the trig ones that kept going and going and going. So there's 2 derivatives. What does the word differentiable mean? Remember, it was that crazy long word, differentiability. I kept telling you guys good luck saying that. Yeah?
You can actually do the derivative.
Okay, so the derivative exists, And what does differentiability also suggest? The fact that they use this word means we know something else. Yeah. It's continuous also. Good. Okay, so if they tell you it's differentiable, you also know it's continuous. Good, good, good. So we have a twice differentiable function defined for all real numbers with the following conditions. F of 0 equals 2, f prime of 0 equals -4, f double prime, meaning second derivative of 0, is 3. So if you were to plug in 0 into the original function, you'd get 2. If you plugged in 0 into the derivative, you get -4. If you plugged in 0 into the second derivative, after you did 2 rounds, you would get 3. Okay, so we have that information. Let's see if we can use that to help us, at least with part A here. The function g is given by, I know it's a little hard to see, but it's e, I'll write it better here, e to the power of ax plus f of x, where a is a constant, meaning a number. Find the value of g prime of 0 and g double prime of 0 if you were to go another derivative round, okay, in terms of a. So we're going to have some a value left in our answer. Show the work that leads to your answers. Okay, so what do you want to try to do here to figure out g prime of 0? What does g prime mean? What is that 0 telling us to do? Can we think about it? What do you think? Yeah.
So if the g is 0, then we know what the fx is going to be, so like we could substitute 2 in right now or whenever we get to the prime.
So if this said g of 0, yeah, we could substitute in 2 because f of 0 would be 2, but this says g prime.
So we could substitute in -4.
Right, eventually, but we have to find the derivative first, okay? So let's go ahead and tackle the first derivative, like in a general sense, and then we'll simply plug in 0. So you need to think about, if you have e to the ax, remember a is a number, how would you find the derivative of that term? Can we remember our shortcuts for the exponentials? The derivative of e to anything is...
Derivative of the exponent times the e to the exponent.
All right, so the derivative of e to anything is simply e to anything. You rewrite the original equation times the derivative of the power. So if the power is ax, where a is a number, the derivative would just be a. Like the derivative of 3x is 3, the derivative of 5x is 5, derivative of -2x is -2. It's whatever that a value is. Okay, so there's the derivative of the first term. We now have to add the derivative of the next term. How do you want to signify the derivative of f? Yeah, f prime. Good. All right, now since a is a number, we can usually move that a value out front as a coefficient. After all, it is a number. So there's our kind of cleaned up derivative. Let's go ahead and think about if we were to plug in 0, what would we get? All right, so if we plug in 0 for the first x, what's e to the 0 power? 1. Good. So we're left with a times 1, which is just a. And if we were to plug in 0 into f prime, do we know what that would be? -4. Notice how that comes from the directions at the top. So it looks like the value of g prime of 0 is a minus 4. Okay, they told you in terms of a, so you're going to have an a value left. That's okay that it's still there. Okay, that's just one part of the problem. They said find g prime of 0 and g double prime. Okay, so let's go ahead and do another round. If this was our cleaned up first derivative, let's go another derivative round and see what g double prime looks like. Okay, so remember, a is a number. If a is a number, the first a that's showing up is like a coefficient, and in terms of derivatives, we keep those coefficients. How do you want to find the derivative of e to the power? Didn't we do that before? It was e to that power times the derivative of that power. So we would have to multiply by another a. Let's go ahead and add the next derivative. How do you want to represent the derivative of f prime? What would the derivative of a derivative look like? F double prime. Good. All right, so if we clean it up, we have a times a, which would be a squared, and then e to the ax plus f double prime. Let's plug in 0 and see what we get. We would have another e to the 0, which is 1 times a squared, which would just be a squared. And then what if we plug in 0 into f double prime? Notice how that would be 3, right? Based off the top. All right, so those are our two values. They're in terms of a. We have a's left over, which is completely okay. But this question was simply asking us to find two derivatives. They were a little tricky because they involve the exponential piece, but we still should be able to figure out the derivatives using our shortcuts. We have to know the shortcuts. Exponentials, natural logs, trigs, okay, power rule, chain rule, quotient rule, all of those, right? Let's go ahead and try to tackle part B. The function h is defined by cosine of kx times f of x. I know the little dot's not there, but if you were to read it, that's how you would say it. This time k is a constant, meaning a number. Find h prime and write the equation of a tangent line, that's not new to us, at x equals 0. All right, so let's tackle the first part. Find h prime. How do you want to find the derivative? Think about your shortcuts. We got a product. We're multiplying two things together. All right, so we have 1 times d2. How do you want to represent the derivative of f? F prime. Plus 2. And then we got to figure out d1. What's the derivative of cosine? We have negative sine of kx and then what? This is a little tricky. Remember, k is a number, like 3 or 4 or 5, whatever you want to put in there. Do we kind of see how this is a hidden chain? You have an inside and an outside piece. So we have the derivative of the outside, keep the inside layer, and then we have to finish off by multiplying by the derivative of the inside. If k is a number, what's the derivative of kx? Just k, right? A little tricky. It was a hidden chain. All right, if you want to leave it like that, that's perfectly okay. If you want to clean it up, by all means, you could do that too. Maybe we'll just leave it the way it is. Okay? Let's go ahead and try to tackle the equation of a tangent line. So we need a point, but also a slope. Okay. We're trying to figure out the equation of a tangent line at 0. So we'll plug in 0 into the original function and see what we get, and plug in 0 into the derivative and see what we get. All right, so in the original function, notice how we have k times 0, which would just be 0. And what's cosine of 0? 1 off the unit circle. Then we have to multiply that by f of 0. Do we know what that is? 2. Isn't that from the top information, right? So it looks like our point value is 2. Let's go ahead and check out the slope. So now that we have the derivative, we're good to go. We just got to plug in 0 for everything. Cosine of 0, we said was 1. F prime of 0, based off the top, we have -4. Then we have to add f of 0, which is 2. What about negative sine of 0? Sine of 0 is 0. And we're multiplying by k. Okay, there's no x attached to that one. So what's the slope value? -4, right. This whole term's going to go away because we're multiplying by 0. So notice how the slope value is -4. Do you guys think you can write the equation of a tangent line with that information? Y minus 2 equals -4 times x minus 0. All right, now here's the thing with the free response questions. Even though there were only 2 parts, every free response question is worth 9 points, just like they are in class. I don't know if you've realized that kind of so far. So even though, for instance, you might not get the correct equation of the tangent line, okay, if you do correct work throughout the process, you still get credit for certain pieces. So maybe you didn't get 2 here, but you still use this number correctly in the equation, they would give you a point for that. Okay, even though this number wasn't correct, you might lose the point from this value, but you wouldn't lose it here. So the moral of the story is, at least with these free response questions that I hope we start to get a little better or confident with, is don't give up. Okay, always try them, never leave it blank. Write something down because there are partial points to be gained for any instance. Okay, just try it, even though you might get stuck. Yeah.
So what if you, instead of doing negative sine kx times k, considering that nulls out to 0, what if you forgot the k but still got the correct answer? Would you lose points for that?
No. No. So like if you didn't even write this here, is that what you're meaning?
Yes.
If you didn't
Because-
even write it, that's okay.
Like how it says h prime of x equals cosine kx times f prime of x, like up there.
Oh.
If you didn't write the
If you miss it here,
yes.
then yes. Okay? So if you miss the k here, you might lose a point. But the fact that you had the wrong derivative, but still use the derivative correctly for the evaluation, you would not lose this point. Does that make sense? If you make,
I mean, you don't even need the k in there because the k gets gnawed out of it.
if you make a mistake but carry it through, you're okay.
Yes.
All right? All right. We'll see you tomorrow.
Have a good one.
You too.
School's starting to step it up all the stuff I know from last year.